Hello, today we're going to be looking at exponentials and logs. Hello, my name is Dr. Islam and let's begin. So, the learning intentions for today's lesson are to understand the properties of exponential functions, to understand logarithms and the laws of logarithms, and to be able to change the base of a logarithm. Exponential functions. Okay, so exponential functions or graphs are in the form of y equals a to the power of x. So a is the base and x is the variable. So these graphs increase rapidly in the y direction and they never fall below the x-axis. They always cross the y-axis at 1. Have a think about this. This is because anything to the power of 0 is 1. So if we substitute x equals 0 into our equation, y equals a to the x, y equals a to the power of 0, so then that would be equal to 1. So it would all of them will cross at 0, 1. An exponential graph looks something like this. So this is the graph of y equals k to the x, and it kind of looks like slowly increases, crosses the y-axis at 1, and then rapidly increases as x increases. So, exponential graphs. I'd like you to have a look at these graphs and think about what patterns you can observe. If you have access to the internet, then on Desmos you can plot different exponential functions. So here I've plotted y equals 2 to the x in red, y equals 3 to the x in green, y equals e to the x in blue, and y equals 100 to the x in black. Can you spot that they all cross the y-axis at the same point? X equals 0 and y equals 1. And can you see they follow a similar general trend of increasing rapidly as x increases? And the speed of increase is dependent on the base. So y equals 100x to the power of x increases much more rapidly than y equals 2 to the power of x. So let's have a look at this. Exponential graphs. What patterns can you observe? I've plotted y equals 2 to the power of x and also y equals 2 to the power of minus x. So if you can, plot on Desmos different exponential functions. So when the power is negative, the graph is reflected in the y-axis. Why could this be? Well, if you think about it, even further, and I said y equals 0.5 to the x, it's also reflected in the y-axis. So why is this? Well, when the power is negative, the graph is reflected in the y-axis. A key tip to note here is that when the base is 0.5, it's the same thing as 2 to the power of minus 1. So y is equal to 2 to the power of minus x. It means it's reflected about the y-axis. So we get a red graph like that, rather a reflection of the blue. This equation can be written in a different form. So y equals 2 to the minus x could be written as y equals 1 over 2 to the x, which is the same as a half to the power of x. So if our base of our exponential function is between 0 and 1, which will be a fraction, the graph will be decreasing. It will have the same domain range intercepts and asymptotes, though, as the other one. There are many occurrences in nature that can be modelled with exponential functions. So let's have a look at another type of exponential graph. So here I've plotted y equals minus 2 to the x, y equals minus 3 to the x, and y equals minus 100 to the x. What patterns do you observe? Well, when the base is negative, the graph is reflected in the x-axis. You might be asked to plot an exponential function by hand. So if I needed to plot the graph of y equals 2 to the x, I would first fill in a table of values. Say when x is minus 2, I'd work out that y would be 0.25, x being minus 1, I'd work out that y is 0.5, and so on. And then I'd plot the pairs of coordinates from the table on a graph, and then I'd get my graph of the exponential function. So all the transformations that you have learned in the past apply to all functions. So if we think about it, if we think about the graph y equals 2 to the x, what would happen if we plotted the graph of y equals 2 to the x plus 3? Have a go in Desmos and pause the video and then come back and show me your answer. So the plus 3, you should have seen that it shifts the graph up by 3. What about y equals 1 minus 2 to the x? Have a think about this. Have a go in Desmos and then check your answer. Well, that minus means that it's reflected over the x-axis, and the 1 means that it's shifted up by 1. So we would end up with a graph that looks something like this in red. And another question. When y is equal to the x minus 2 minus 1, what would happen to the graph of y equals 2 to the x? Pause the video and go and have a go in Desmos and come back and see if you got it correct. Well, the minus 2 in the exponent means that it shifts the graph to the right 2 places. The minus 1 means that it shifts the graph down 1 space. So you would end up with a red graph like this. If you need more practice, I would suggest plotting many different graphs in Desmos and seeing the relationships and patterns that emerge. Now I'd like you to do some practice questions. Pause the video and have a go. Okay, here's the answer for the first question. So it said complete the table of values for y equals 3 to the x. So you substitute x equals minus 2 into the equation and you'd get 1/9. Substitute x equals minus 1 and you'd get a third. Substitute x is equal to 0 and you'd get 1. Remember, every exponential function would be crossing through the point 0, 1. And when x is equal to 1, y is equal to 3, and when x is equal to 2, y is equal to 3 to the power of y is equal to 3 to the power of 2, which is 9. So then you should have plotted your points on a graph or on a squared paper, and it should look something like this. So for question 2, the question asks, draw the graph of y equals a third to the power of x for the values of x from minus 4 to 4. So the first step would be to realise that a third x is the same as 3 to the minus 1, 3 to the minus x. So we are needing to plot the values of the graph when we substitute in our values to 3 to the minus x. So if we need to do everything from minus 4 to 4, so it would be good to have chosen minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and 4. And I've got the solutions there for you. So it goes from 81 to 1 over 81. So you should have plotted those. And as you can see, of course, it crosses the y-axis at 1. And it is, because it's 3 to the minus x, it's reflected. It's the reflection of 3 to the y equals 3 to the x in the y-axis. And lastly, so the extension question said, The sketch shows a curve with an equation y equals ab to the x. So that just means a is a value and b is a value and b is to the power of x. And a and b are constants and b is greater than 0. So that's really important. So we know it will be greater than 0. So it's going to be in that general form that we would think of the curve. Okay, so we have more information. We have the curve passes through the points 0, 3 and 2, 12. Calculate the value of a, b. So when x is equal to 0, y is equal to 3. So we'll substitute those values into our equation. So we will have 3 is equal to a times b to the power of 0. Now, anything to the power of 0 is 1. So it would be y is equal to a times 1. And y, as I said before, was 3. So 3 is equal to a times 1. So a is equal to 3, or 3 is equal to a. So we've found that first bit out. Then I'd use my second point. So I've got the point 2, 12. So substitute again. So we've got the equation y is equal to ab to the x, and we know that a is 3, so y is equal to 3b to the x. So we're going to substitute x is equal to 2 and y is equal to 12 from that second point that was given in the question. So then we have 12 is equal to 3 times b squared. So then we just want to work out what b is. So we don't want 3b squared. So we have to divide both sides by 3. So 12 divided by 3 leaves us with 4. And then 4 is equal to b squared. But we want to know what b is. We don't want to know what b squared is. So we're going to have to square root both sides. So this b is equal to the square root of 4, which is equal to 2. And the answer could have been minus 2, but if we go back to our question, it says where a and b are constants and b is greater than 0. So it can't be minus 2, it has to be the positive solution, so it has to be plus 2. Okay, so let's have a look at the graph y equals 2 to the x. So first of all, we need to plot this graph. So we substitute x is equal to minus 2 and we get y is equal to 0.5. We substitute x is equal to minus 1 and we get y is equal to 0.45. We substitute x is equal to 0 and we get y is equal to 1. When x is equal to 1, we substitute when x is equal to 2 and when x is equal to 3. So we've plotted these points and then we can sketch our graph. So this type of graph or function is known as an exponential function, and it's very useful for modelling things like population growth or savings with compound interest. The key property of exponential growth is that the output gets multiplied by some constant each time the input increases by a unit. For example, with a rabbit population, it might get 40% larger each year. This is in contrast to linear growth, which would look like a straight line where we add some constant each time. This time, our output's getting multiplied by a constant each time. A logarithm is the actual exponent or the power. So the key thing to remember is that the logarithm is the power. So logarithms are written as log, a little a, b is equal to x. And we say this as log base a of b is equal to x. And that means that a, the base a, to the power of x is equal to b. So I'll repeat that. So log base a of b is equal to x. That means that a to the power of x is equal to b. So this might help us in situations where we've got something to an unknown power and we want to know what that power would be. So a really simple example is 2 to the power of x is equal to 8. So we know already very simply that 2 to the power of 3 is equal to x, so x is equal to 3. So in log form, we could write this as log base 2, because that 2 is the base, of 8 is equal to 3. So the power is 3 and the base is 2, easy enough. And the number 8 is what we're taking the log of. So the log base 2 of 8 is equal to 3. Now logs or logarithms are the inverse functions of exponential functions. So if you think about it, if we start with 4 and we put it to the power of 5, we end up with 1024. To go backwards, back to 4, we need to find the fifth root. In our second example, we've got 4, and then we do 3 to the power of x, and we end up with 81. So to go back to 4, we would need to do log base 3 of x, and that would take us back to 4. Okay, it's the inverse. So if we had 4 and then we did e to the power of x, we'd end up with 54.59. So to go back to 4, we would need to do the inverse operation, and that would be taking the natural log, the log base e of x, which we write as the ln x. ln x is the natural log of x, and we usually write it as an ln rather than a log base e. So logarithms are log a of b is equal to x, means that a to the power of x is equal to b. So the logarithm is the power. So since the logarithms are the powers, we can define the following laws of logarithms. So if we had log base a of a, well, what would that be? Well, the base is a, and we want to know which power we raise a to get a. So that would be 1, because a to the power of 1 is a. So for example, if we had log base 7 of 7, we would raise 7 to the power of 1 to get 7. So therefore the log base 7 of 7 is 1. The second law of logarithms, let's have a look at log base a of 1. So this means, what do we raise a to the power of to get 1? Well, if we remember from our law of indices, anything to the power of 0 is 1. Therefore, log base a of 1 is 0, since a to the power of 0 is equal to 1. So, for example, if we had log base 20 of 1, well, 20 to the power of 0 would be 1, so log base 20 of 1 is equal to 0. Remember, the log is the power. So, reminding ourselves of, think back to those law of indices. When you were multiplying with the same bases, you add the powers. When you were dividing by the same bases, you subtract the powers, and so on. So if we had log base a of p plus log base a of q, what are we doing there? Well, we're adding the powers. So that would be the same as log base a of p times q. And so, for example, if we had log base 3 of 2 plus log base 3 of 5, that means that your base is 3, and what do you have to raise 3 to get 2, and what do you have to raise 3 to get 5, and you're adding those powers. That would give you the number you need to raise 3 to get 2 times 5, 10. So that would give you the log base 3 of 10. So the rule, which comes from the fact that when we add the powers in multiplication, when you add logs with the same bases, you can write that as log that same log base of p times q. So log base a of p plus log base a of q is log base a of p times q. Remember in algebra, pq means next to each other, it means p times q. So here we had log base 3 of 2 plus log base 3 of 5, and that's log base 3 of 2 times 5, which is 10, so log base 3 of 10. So with addition, it became multiplication. So subtraction would become division. So log base a of p subtract log base a of q would become log base a of p divided by q. Okay, so log base 6 of 54 subtract log base 6 of 9. Well, it would be log base 6 of 54 divided by 9, which is log base 6 of 6, because 54 divided by 9 is 6. Now, if we think back, log base 6 of 6, what do we raise 6 to get 6? It's 1. Anything, any time you've got the base and those two 6's being the same, it's 1, because anything raised to the power of 1 is itself. And finally, log base a of p to the power of n. So this is where we're going to be thinking of the law of indices. When we raised a power to another power, we ended up multiplying. So by the same logic, log base a of p to the power of n, that n ends up as a multiplication. So we can extract that n and it becomes n log base a of p. So for example, if we had log base 2 of 5 cubed, remember raising a power to a power, we multiply the powers. So that 3 that we've raised that 5 to can come down and it's multiplying, becomes a multiplication. So 3 times log base 2 of 5. So and we just say 3 log base 2 of 5. So these are really important to remember and understand the laws of logarithms. You're going to be using those when you answer questions, and I would suggest you write these down in your book as a reference. You may get a question which involves changing the base of a log. So the formula for changing a base of a log from the base b to base x is log base b of a is equal to log base x of a divided by log base x of b. So why does this work? Well, I'll show you in the next slide. So we've got changing the base of logs. So we've got our formula there. Log base b of a is equal to log base x of a divided by log base x of b. So why does this work? So we want to show, for example, in this example today, we're going to do log base 10 of 4 is equal to log base 3 of 4 divided by log base 3 of 10. Okay, so compare that to our change of base logs. Yep, we've got going from base 10 on the left-hand side to going to base 3 on the right-hand side. So my first step will be to, let's, for example, say that n is equal to log base 10 of 4. So that we're saying that n is going to be log base 10 of 4. So what does that mean? Well, that means that 10 to the power of n is equal to 4, because remember the logs are the powers. So that statement means that 10 to the power of n is equal to 4. If you're unsure about this, then go back and relook at the definition of a log. But from the definition of a log, we've got that if n is equal to log base 10 to the 4, that means that 10, that base to the power of n, is equal to 4. So if we take logs on both sides, and we take log base 3 of both sides of our equation, we get log base 3 of 10 to the power of n is equal to log base 3 of 4. So all I've done in that step is I've taken log base 3 on the left-hand side, and I've taken log base 3 on the right-hand side of the 10 to the power of n equals 4. Okay, so my next step would be to use the power rule. Remember, when we've got a log to the power, we can bring that power down to become a multiplication. So using the power rule, we've got that n times log base 3 of 10 equals log base 3 of 4. Okay, so we're getting closer to what we want to prove. Now, what I want to show is the next step, which is dividing both sides by log base 3 of 10. So if we do that, then we get n left on the left-hand side, and on the right-hand side, we get log base 3 of 4 divided by log base 3 of 10. The last step we're going to do is to substitute our value for n. So n, remember at the start, we said that n is equal to log base 10 of 4. So instead of n, we're going to put log base 10 of 4. So therefore, we get log base 10 of 4 is equal to log base 3 of 4 divided by log base 3 of 10. That's an example for changing the base of a log. So today we looked at the properties of exponential functions and graphs, and you should be confident now about how to go about plotting an exponential function or graph. And we looked at logarithms and the laws of logarithms, and we also looked at how to change the base of a logarithm. What I'd suggest you do now is go and do some practice questions to test your understanding. Well done. See you again next time.